This is Function and Analysis Part 1 assignment. I like to go through question 1 of the assignment with you just because this is a long, involved process. You should watch the video that takes you through the notes first before you start the assignment. I've already filled in some of the information. Make sure you run these things that are already filled in. You're going to need them in other parts. So first thing, as we move to question 1, we're trying to analyze this function, looking at all the different ones. We're not going to work together in class. We're going to work on it on this video. So here I am. I'm going to run this line, make sure the function is in there. I have it shown just to make sure we typed it right. Now notice that they actually, for whatever reason, factored this 5 out, so you kind of have to mentally adjust, but that is the correct one. Okay, now we need the domain of this function. Now here in part 1 of function analysis, the domain of all of these is going to be all real numbers. We will deal with domain issues in the next assignment, function analysis part 2. All right, so the derivative. Let's go ahead and run that, make sure that's in there. I'm going to show the derivative as well. This is mostly so I can check the domain. So this week we're only going to have domain all real numbers, but that is in step 3, that is a relevant thing to check. Where is the derivative undefined? And so we'd have to check this formula, see if there's any domain issues. The only potential thing here is division by 0, but you'll notice that the denominator here is x squared plus 110 is never negative. It's at least 110. This is at least 110 squared. We're never dividing by 0 here. So all we need to worry about for the critical points is where the derivative is equal to 0. So I asked the computer to solve that for us. So I called the derivative df up here. So I said, where's df equal to 0? Solve for x. That's already there for you. Now we get these two messy answers. We should really convert those to decimal with the capital N command. Now there's two ways to do this. If you're able to copy and paste, see that what happened? That often happens to me. Copy and pasting just doesn't work. Oh, I think I got it there. So sometimes it works better from the back side than the front. But sometimes copy and paste just doesn't work very well for whatever reason. I don't know if it's a browser issue, a computer issue. So you saw when I tried to highlight this one at first, maybe because I got off, maybe I didn't go straight enough. Who knows? I haven't been able to figure out any rhyme or reason to that. So if you are able to copy and paste, that's the easiest way. And so you can certainly do that. Now if you have trouble like I did with copying and pasting, let me give you a second way to do that. You can access this information directly in the computer. To do that, I'm going to give this solution set a name. So when you do solve, out comes this list. These square brackets here indicates a list in CoCalc. So a list comes out. So S now is a list. Now if I run this, then nothing's going to show up because the answers got plugged into this S. So let me go ahead and say S, it'll print it out. Okay, so here is the answers. Now, I'm going to take this away. I want to convert to decimal the things inside this list S. Now I cannot just say convert S to decimal. It does not understand that I want each part to go to be a decimal. I need to access each one of these list items individually. So in CoCalc, the first item in a list has index 0. So this is how you access particular items in a list. You put the list name, S, and then you put square brackets, and that's where you put the list item you want. So S bracket 0 is the first item. Now if I run this, I will still get an error because S bracket 0 is not a number, it's this equation right here. So I don't want that, I just want the right-hand side of that equation. And so here's how you get the right-hand side of an equation. S bracket 0 is an equation, you put a period after it, and then RHS for right-hand side, and then parentheses. Now, if you've programmed in Python before, this should look familiar to you. If you haven't, well, I haven't either, so this is strange, but that's the way it is. And the second item in the list is list name, bracket 1, dot right-hand side of that equation. Okay, so copy and paste if you can, because that's a lot simpler. But if you're having trouble copying and pasting, you can use this method to get at individual answers here. Now if there's more than 2, then of course you would have to continue this on. S bracket 2 would be the third item, and so on. Okay, so these are the 2 places where the derivative is equal to 0. So those are the critical points here. Those are our potential mins and maxes. What we want to do in step 4 is to see if they are actual mins and maxes. To do that, we need to see if the derivative changes sign. So I'm going to start with this first one, negative 10.4 roughly, and I'm going to choose a number to the left of that and plug it into the derivative. So the derivative I called df up above, and something to the left of that like minus 10.5, for example, or you could do minus 11 or whatever you want. I'm going to choose something to the right of that. How about minus 10 is good enough. Now notice what happened. I'm just checking the sign here. It was negative to the left of my critical point, and it's positive to the right. That means that the original function f was decreasing to the left of my critical point and increasing to the right. So decreasing changes to increasing. Draw a little picture with your hand. Decreasing changes to increasing. Okay, do you see I'm tracing out a local minimum? What that means is that f, oops, not got f has a local min at x equals approximately negative 10.38. Okay, and now we go to the second critical point, around 10.6. I need to choose something to the left of 10.6. How about 10? I need to choose something to the right of 10.6. How about 11? Okay, it's positive to the left and negative to the right, so that means it's the original function is going up and changing to down. I'm making a peak. This is a local maximum. So the original function f has a local max at x equals 10 point, what was it equal to? 10.59, about 10.60. Okay, now I would suggest that you might have a piece of paper here with you when you're doing this, and these critical points are going to come up at various places. So I like to keep track of places where the function itself is 0, where the derivative is 0, and where the second derivative is 0. Those numbers are going to be relevant down in the final step where we do the increasing, decreasing, and all that stuff. That's the step I'm actually going to grade when I check this assignment. So it's important you have all those numbers available. Rather than scrolling back and forth all the time, I would suggest that you write down on a piece of paper f prime equals 0 when x equals negative 10.38 or x equals positive 10.60. And you might even record that negative 10.38 is a min and 10.60 is a max. And when we graph it, we'll check and make sure that all worked out right. And we'll make sure we see those on the picture. If your picture doesn't reveal those things, then either you made a mistake or you need to change your picture. Okay, so first derivative helps us find mins and maxes. Now we're on to the second derivative. So I've already done it for you, but let's go ahead and make sure you run that so that it's in there. We're going to use it later. Here is the what the second derivative looks like. Again, I want to check the domain here in step 6. Is the second derivative undefined anywhere? The answer is no. We never get division by 0. That's the only potential problem here. All right, now we need to find where the second derivative is 0, and there's a big mess of places. So here's one, all the way to the comma. That's the first answer, and then x equals blah, 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 all the way to the second answer, and then x equals blah, blah, blah. Okay, there's 3 answers there. Now, I'm not even going to try to copy and paste. If you can copy and paste, great. I'm not going to try. I'm going to go ahead and do it this sort of longer way. So I'm going to have s bracket 0 and right-hand side, and I'm too lazy to type that over again, so I'm just going to copy and paste, and I'm going to change this. There's actually a way to sort of automate this to print out, to convert to decimal all the right-hand sides, but that's not worth it. There's only 3 of them. So At first glance, these three numbers look like they are complex numbers. See this I stuff over here? That's imaginary numbers. And in fact, maybe we should even show, let's see what it looks like if we show this solution set. See that there's this I in here at various places. So I is the square root of -1, okay? Imaginary number. We don't care about imaginary numbers. Those don't show up on our graph. But the problem is CoCalc is kind of lazy. It's very possible that if we were to simplify this huge mess, all the imaginary stuff would cancel out. Now, there's no guarantee of that just looking at it, but it might. So we need to, these look like they might have imaginary stuff going on, they might not. So when you see this here in the decimal approximation, I see the I on the end. This looks like imaginary stuff, but look at this. E minus, I can't even highlight it. E minus 15. That is scientific notation. That means take this number 5.32 and multiply by 10 to the minus 15 power. Now that means the number is not 5.3 but 0.0000000, 14 zeros and then the 532. So that is a very small number, very close to 0. Now there's two possibilities. Either this really is an imaginary part here and this is a complex number we should ignore. That's possible. Or more likely, this puny number is rounding error, and when it did the decimal approximation, the i's should have canceled out, but they didn't quite, just due to rounding. Whenever you see e minus 15 or 20 or 12, something like that, e minus 1 or 5 even, that's not small enough. But you see something in the teens or 20s, that's probably just rounding error. So we'll check that in the next step, but be on the lookout for scientific notation. If imaginary stuff shows up, it may or may not be relevant. So, in fact, in this one, the second derivative is 0 when x is roughly 0.04. Okay, this is 0.04 here, and this imaginary stuff is really rounding error. And then when x is approximately negative 18.02, and when x is approximately 18.31. And I'm writing those down on my scratch paper because those are going to show up again later. Okay, so in step 7, I'm going to see if the sign of f double prime actually changes. So I'm going to take, what did I call this? D2f is what I normally call it. Yeah, D2f is what I named the derivative. So we should use that name, D2f, not W. D2f is the second derivative. I'm going to choose something to the left of this. How about 0? I'm going to choose something to the right of this. How about 1? Did the sign change? Yes. So the original function f changed from concave up. Remember, positive second derivative means concave up function. Here's negative second derivative. That means concave down function. So the original f has an inflection point at x equals approximately 0.04. That's what this means. When the second derivative changes sign, f has an inflection point. F changes concavity. Now, by the way, that confirms what I suspected, that this was rounding error, because if this were not, that wouldn't happen. Okay, so the second derivative can only change sign at a critical point. So there must be a critical point between 0 and 1. Now, perhaps I should make a comment about this point about choosing things to the left and right. I chose something to the left of 0.04 and something to the right of 0.04. How do I know how far to go? Well, the only requirement when you go to the left and right is that you cannot interfere with any of the other numbers on this list. So if I chose negative 20 here as something to the left, is that to the left of 0.04? Yes, it is, but it's too far to the left because there's another number on the list, negative 18. That's past the next number. So you have to choose something between the two. Now, in this case, it's not that hard. In some cases, if these critical points are really close together, you got to be cautious that you're not making your, going left and right too far. This one, it's not that big a deal. Okay, let's take the second point. I need to choose something to the left of negative 18. So, oops, d2f, second derivative. How about negative 20? And something to the right, how about negative 17? Okay. Now, by the way, if you have trouble with these, you might be able to convert to decimal just by using the decimal. In fact, you don't even have to put anything after the decimal point. If you put a decimal point in there, then decimal goes in, decimal comes out. So if you don't like the fractions, sometimes it'll give you an exact value, something messy in other problems, and it might be hard to tell if it's positive or negative. So maybe decimal goes in, decimal comes out. If there's still something exact there, you can always use the capital N command to convert to decimal. Again, all we want to see here is, does the sign change? Negative changes to positive. Yes, there is a sign change, which means the original function, why do I keep capitalizing it? The original function f has an inflection point at x equals negative 18.02. Okay, now we got the third one, 18.31, and that's the last one to check. So something to the left of that, how about 18? Something to the right, how about 19? Negative change to positive, yes, there's an inflection point there, so I'll just record that here. F has an inflection point at x equals 18.31 approximately as well. Okay, I'm writing these little notes to myself just so when I come back and look later, I'll see what it is I did. That's the purpose of these calculations. Like we did in the lecture, we had the test point method, we drew a number line, and we tested different points. That's what we're doing here. I didn't draw a number line because it's hard to draw a number line on the computer. I mean, I could have done it on my paper and saved myself trouble. You see there's some redundancy here because things that are to the right of this one are to the left of this one, and so I've kind of been redundant and doubled up my work some. But avoiding that redundancy would require thought, and I don't really want to think. The computer does these calculations so fast, I'm fine doing extra work here. So the main point, though, checking the sign of the second derivative is to see where the inflection points are. Okay, so all three of these are inflection points. So if you wrote these three x values down on your scratch paper, I would put a little IP for inflection point next to them just as a reminder that the concavity changes. So when we get to the graph, we want to make sure that we see the concavity change. All right, now the x and y intercepts I already did, where the function is 0. So 1/9 is the x-intercept. You might want to write that down too on your scratch paper. When x is 1/9, it crosses the x-axis because we want to make sure our graph shows the x-intercepts. Now, this is the first y value we've seen so far. Every y value you've calculated so far has been either for the derivative or second derivative. This is the first y value for f, and we want to make sure that shows up on the picture. You might write that down on your scratch paper as well. Make sure that when you graph it, this number shows. Okay, now end behavior depends on the domain. This one is domain all real numbers. So for end behavior, we want to take limits of the original function f as x approaches infinity. You can type out the word infinity, or you can put two little o's. Okay, that's an o, not a 0. And we want to take the limit as x approaches minus infinity. Here, this one I'll write out just so you can see the two different infinity. You can do it either way. Two little o's represents infinity. I could put two little o's there, or I could type it out there. You do whichever one makes the most sense to you. Okay, because the ends of the domain are infinity and minus infinity, that's why we're taking these two limits. If the domain had some sort of restriction, if the domain was only from 10 to 20, then you would see what f did at 10 and 20. Now, what does this mean? When you have limits at infinity or negative infinity and you get a number out, that means you have a horizontal asymptote. So the function f has a horizontal asymptote at the horizontal line that's y equals 0. Now that is the x-axis, by the way, so we should see the graph approach the x-axis when x gets huge in either the positive direction or the negative direction. Okay, now we want to make an informed graph. I look down on my list of all those critical points I got from the first and second derivative and my x-intercepts. I want to see the largest and the smallest x values that are on there. Now the smallest x value of all those I've written on my scratch paper is the inflection point at negative 18. So I'm going to plot here, plot the original function f. My x min needs to be somewhere to the left of negative 18. Let's start with negative 20 and see what happens. All right, the biggest x is the inflection point at positive 18. I'm going to go to 20, see what happens. Now what should I do for my y min and max? I could let the computer choose it for me, and it might be okay in this example. In some examples it's not okay, especially when there's vertical asymptotes. In this one it would probably be fine, but I want to kind of come up with a general method here to deal with this, any kind of function you might come up with. And so I'm going to go ahead and choose the y min and max. How am I going to do that? Well, I need to have some idea of what y values come out of this function. I have the y-intercept, the negative 1 over 22. I need to know what y values go with all my critical points. So I'm going to take my original function. I'm going to plug in those places where the derivative was 0, and I'm going to plug in the places where the second derivative was 0. Now I don't need exact values here. I'm just looking for round estimates for the size of this function. I want to make sure my graph shows all these critical points, the inflection points and the mins and maxes. So I want to make sure my x range here covers all the x values that I wrote down, and then I'll choose my y min and max so that it covers all of these y values. So this was the local mins and maxes I found, and this is it just above negative 2 and 2, and here's the inflection points. So maybe I'll choose, if I want to keep a whole, like an integer, I'll choose -3 and 3. Those will end up being a little bit bigger than I need. Let's start with that. Now you can always change, but here's the first picture. Okay, I see my local maximum there, 10.6, where that's supposed to be. That looks about right. I see my local minimum, negative 10.38. Okay, that looks about right. I see an inflection point here close to 0. Okay, 0.04. That looks about right. You know, this is concave up here. This is concave down there. Now on this picture, you might think, okay, this looks like it's concave down and it just stays concave down. Now we know that's wrong because we know there's an inflection point right in here somewhere, 18.31. Does it look like there's an inflection point? No. Well, it's because we haven't graphed far enough. We need more over here. So it's always dangerous to put an inflection point right near the edge. So 20 wasn't enough to show the bend there. Okay, this is concave down. It has to be concave up right here in this little chunk between 18 and 20. So I need to go further. Let's try 50. The other thing that doesn't show up on this graph is the horizontal asymptote. Remember I told you that there's a horizontal asymptote at the x-axis, and it's kind of getting towards there, but not very close yet. Now on this window, do you see some bend? This is definitely concave down here. This is definitely looking concave up. Okay. Now you could go further, and there's sort of an interplay between seeing kind of the big picture and seeing what happens in the middle. So here's out to 500 both ways. The inflection point here at wherever 18 is, somewhere in the middle here, is very clear. This is definitely concave down. This is definitely concave up. This horizontal asymptote is becoming clear, so that's good. The disadvantage of this window is everything right here in the middle is kind of crammed up. So I don't know. There is no one right answer. You choose the window that you think best shows you this picture. I think that 100 is a good compromise. We're starting to see the the horizontal asymptote. We can see the mins and maxes and inflection points. So that's good. Now I would like you also to add some points on here. All those important points I want to see on this picture. So to do that, we'll use the point command. So add on points. Now I don't want just one point, I want a whole list of points. So to get a list, I need square brackets. Square brackets is a list. Within this list, I'm going to add the points I want to graph. So let's start first off with the mins and maxes. So x was negative 10.38. And the y value, either you can go back up here and see what the y value was from that. F of 10.38, that was the first one. That's this guy, negative 2.17. Or the alternative, let's do that with 10.6. The alternative is to have the computer recompute it right here. You just say f of 10.6. Now make sure you get enough parentheses. You need one parenthesis for the f function and one parenthesis for the point. You can do it either way. Since I already calculated them up there, I'll just go ahead and use the numbers that I calculated. They are in order, so just so long as you keep these things in order. And probably we don't need 2 decimal places. We're not going to be able to tell the difference on the graph, so I'm being a little bit overkill here, but that's okay. If you don't get enough accuracy, the point will will miss the curve a little bit. So get in all these important points. So I got my mins and maxes and inflection points. You should also add in the x and y intercepts. So the x-intercept was 1/9, and the y value is 0. And then when x is 0, the y value was -1/22. Okay, now when you do that, the default is kind of small. So I like to do 2 things. I like to change the color, and I'm going to make mine black. But you can make them whatever you want. Oops. It doesn't matter if you use single quote or double quote. You use the same at both sides. And you can also change the size of this. Let's see. 50 may be a little bit too big, but you can experiment, see what size you like. Now, right here, there's this big glob because there's 3 different things going on there. The x and y intercept and one of the inflection points are all here, close to x equals 0. None of them are the same, but they're close together. Now, if you really wanted to see those distinguished, you would need to make a much closer picture. But this is good overall. So depending on what you want, if what you really care about is what goes on here, you can make it close up. But I want to see the change in concavity, and I want to see the change in direction. Okay, so here's a decent picture, compromise between the different things we're trying to look at. Now I'm going to use this picture to ask where is the absolute max, and where is the absolute min, and where is the function increasing, and where is the function decreasing, and where is the function concave up, and where's the function concave down. Now I'm going to, this little pound sign in front, it tells it that it's a comment. So if I accidentally hit run, it won't give me a big error. You don't have to do that, but then you won't be able to run. Okay, so look at the picture. Does this thing have an absolute maximum? Yes. This local max is actually the absolute maximum. Now, how do I know that? How do I know this function doesn't turn around over here somewhere at 1,000 or at 1,000,000 or at 10 billion? I know the function turns around because if it turned, there would be a local minimum. And there is no local minimum over there. I have all the local minimums drawn here. It's there. All right, that's why we did all this analysis. We know that this picture shows all the important features. There's no local min or max or inflection point anywhere else. So this cannot turn around and go up. Now what about here? Can this just keep on going up forever and eventually get higher than this local max? No, it can't, because we know that this is a horizontal asymptote. We know that there's no x-intercepts over here, so it doesn't cross the x-axis and then come back. Of course, to come back, it'd have to turn, and we know there's no turning point. Turning point would be another local max. So this just goes up and flattens out along the x-axis, so it never gets higher than 0. So this is the peak. And where was that? We can go back up here to our calculation. The local maximum is this one, 2.12 approximately. So the absolute maximum is approximately 2.12, and it occurs at that local maximum of x equals 10.6. Now, similar reasoning shows us that this local min is actually the absolute min. So back up here, the absolute min is negative 2.17 approximately. And that occurs at the local minimum, which is approximately negative 10.38. Now, if you want the exact values for x, you can go back up to the first derivative, where we found out where the first derivative was 0, and you can read the exact values. You can put those into the function if you want and get the exact value of the min and max if you really want to, or you get a better decimal approximation if you would use those. That's okay, we don't really need that here. All right, where is this thing increasing and decreasing? I'm going to start here at the left side and just go along from left to right along the x-axis. So right here, the function is going down. So it's decreasing, starting over at negative infinity, which I'll go ahead and abbreviate with these double O's to make a little infinity looking thing. It's decreasing until it hits the minimum. That's where it turns around and starts going up. So it stops decreasing right here. Where is that? I look on my little scratch sheet again, negative 10.38. That's where the local minimum is. That's where it changes direction. Okay, notice what I'm writing here is an interval of x values. There is no y values here. I did not say y changes from 0 down to negative 2.17. I don't care about that. That's not what I'm saying. When I'm asking where the function is decreasing, I'm talking about x values. When x goes from negative infinity up to negative 10.38, then the function is going down. Okay, once I hit this local minimum, it turns and goes back up until it hits the peak. So it starts increasing at negative 10.38, and it keeps going until I get to the 10.60, the local max. Now, by the way, I could put square brackets on these intervals, and that would be true. I'm not really concerned with that, so I'm just going to go ahead and use parentheses because it doesn't matter to me. In Calculus 1, it's just not that big a deal. So you can put square brackets if you want to, but you certainly don't have to. All right, after this peak, it's heading down again. So 10.60, it starts, and it keeps going down, down, down forever after that to infinity. Now notice that these numbers, the boundaries in the increasing and decreasing, are the local mins and maxes, the places where the first derivative is 0. The inflection points have no business here. Okay, so the inflection point should never show up here. The x and y intercepts don't matter here. What matters is the places where the derivative is 0, these local mins and maxes. And notice also that the entire domain needs to be covered. So I start at negative infinity, I reach negative 10, I pick up again at negative 10 and go to 10, I pick up at 10 and then go on to infinity. All real numbers have to be in one of these somewhere. Unless, of course, there was a constant section, which is not going to happen for any of these examples. All right, we're almost done. Concave up and down. Again, I'm going to start on the left. It starts out concave down on the left. Okay, put your hand on here and your palm will point down. And or if you imagine tangent lines here, this is below the tangent line. Okay, so concave down over here to the left until it hits the first inflection point. That's negative 18.02. Inflection points are where the concavity changes. Okay, don't let me see any of these mins and max numbers. These tens things, those guys don't belong in the concave up and down. Just the inflection points do. Okay, at that inflection point, it changes to concave up. So back to concave up. And it stays concave up till it hits the next inflection point, which is there, 0.04. And then, of course, since that's an inflection point, it changes to concave down, 0.04. It stays concave down until it's the next inflection point, which is the 18.31. And after 18.31, it's concave up again, and that keeps on going. There's no more inflection points. Okay, so increasing and decreasing has the min and max numbers. Concave up and down has the inflection point numbers. Okay, these are intervals of x's, no y values here. Okay, these are the y values. Absolute max is a y value, absolute min is a y value if they exist. Those are the only y values down here in step 11. Okay, now make sure when you're doing number 2 on your own that you get a graph and you fill in step 11 because that's what I'm going to grade. So if you do all the work above and got nothing here, you're not going to get any credit. Okay, so the point of all the work above is to produce a decent graph and to analyze a function. These are kind of the key features of the thing. So make sure you finish step 11. Okay, so question 2 I'll leave for you to do on your own. Be on the lookout. The function g has 2 x-intercepts, and when you solve g of x equals 0, you will get 4 answers. Only 2 of those are real. 2 of them are actually complex numbers. Okay, you can ignore complex numbers. Convert to decimal. Watch out for scientific notation. That's similar to what we did up here. Okay, so in the g function number 2, Some of the answers will have scientific notation and some of them won't. So be on the lookout for that. I call this function g just to distinguish it from the one above. Make sure that you use g now. Don't use f down here. That's for number 1. Got any questions? Let me know.